All right. So today we're going to talk about the alkene additions that involve carbocations, including hydrohalogenation and hydration. So we're going to be going over first the concept of carbocations and carbocation stability, and then we're going to move on to the first reactions, how to draw reaction mechanisms, and predict the product when it comes to these reactions, including things like carbocation rearrangement, such as hydride shifts, methyl shifts, and ring expansions. So generally, these are the first alkene reactions you learn in Orgo 1 curriculum, and so this video will highlight those first carbocation reactions. So before we do anything, let's talk about what a carbocation is. So a carbocation is when you have a plus charge on a carbon. Now, this is one of the only times in Orgo 1 where we see something that violates the octet rule. So the octet rule says that every atom needs to have 8 electrons on it at all times. So if you look at this carbon right here, this one does not have a plus charge. It has 1 carbon, and every carbon, if it has no charge, has to have 4 bonds on it. That means that there are 3 implied hydrogens if I have a total of, I have a total of 4 bonds. Now, I have 4 bonds total, 1, 2, 3, 4, and every bond is 2 electrons, so 4 bonds, 2 electrons in each bond, so I have a total of 8 electrons on this carbon. Same thing with this one here, but what about the plus charge on the carbon right here? So a plus charge on a carbon indicates it has only 6 electrons. That means it only has 1 hydrogen on there. So it has 2 bonds previously to carbon, 2 electrons there, 4 electrons from those 2 carbons combined from those bonds, 2 there, 2 there. Now this one has 2 electrons as well. That has 6 electrons. That means I only have 1 hydrogen on this carbon because a plus on a carbon implies that I have only 6 electrons on there. So a carbocation is a positive charge on a carbon. So the rule of thumb as far as what makes carbocation stable is that the more carbons attached to the carbon with a plus, the more stable it is. So for example, let's take the carbon with a plus charge here. This would be considered a tertiary carbocation because the carbon with the positive charge is bonded to 3 other carbons, 1, 2, 3. This would be a secondary carbocation because the carbon with the plus is bonded to 2 other carbons. This one would be a primary carbocation because the carbon with the plus is bonded to 1 other carbon. Now, the worst carbocation would be a methyl carbocation. This doesn't even really exist because having a carbocation where there's only 1 carbon on there is wildly unstable. So this is a general trend for carbocation stability. It does get a little bit tricky when we start to involve benzene rings, but we're going to talk about that towards the middle of the video. So for right now, though, if we have a plus charge on a tertiary carbon, that's the most stable compared to secondary compared to primary. So let's kind of go through a generic first example of a carbocation reaction. So I'm going to have an alkene. An alkene is a carbon-carbon double bond. And the first reaction we're going to talk about falls under the category of hydrohalogenation. Hydro because hydrogen, and halogenation because halogen, bromine, chlorine, or iodine you can add to a carbon-carbon double bond. So the general gist, I'm going to draw the product first, and then we're going to figure out how we got to that product. So the general gist when you have an alkene reaction is that you're starting off with a double bond, you're getting rid of the double bond at the end, and you're adding a group to it. You're adding 1 group or 2 groups. So technically here, I'm adding a bromine to this carbon, and I'm adding a hydrogen to this carbon. So I'm adding a bromine and a hydrogen, but I don't have to draw in hydrogens. So this would be an acceptable answer to this question. So let's kind of figure out how we got to this answer by going through the reaction mechanism. So the mechanism is basically an electron movement, showing electron movement that explains how the product is formed. So let's draw out the mechanism for this reaction here. So the most important part about drawing mechanisms is that whenever you are drawing a mechanism, every arrow you draw has to come from a source of electrons. So the very first step for this reaction, when you have an alkene with HBr or HCl or HI, the very first step is that the electrons that are in the pi bond, that are in the double bond, one of the bonds here is going to grab a hydrogen. And whenever something grabs, whenever you show an arrow like this, it means you're forming a new bond. So that means that I'm forming a new bond between this structure and this hydrogen. So what's going to happen next is hydrogen is only allowed to be bonded to one thing at a time. So it's bonded to the bromine first of all, but if the double bond, if this structure here grabs it, that would imply that now this is being bonded to the H. That means that if this is now being bonded to the H, the bromine can no longer be bonded there. So the electrons between the H and the Br are going to go towards the bromine. So let's think about this. The bromine used to have a neutral charge, but now it's gaining electrons. In every single bond, there's 2 electrons. So the 2 electrons are breaking onto the bromine. The bromine is gaining electrons, so it gets a minus charge on it. So it has a negative charge. Well, what happens to this structure here? Well, you are forming a bond between one of the 2 carbons in the double bond to the hydrogen. So let's think about the possibilities we have here. If I call this carbon in double bond carbon 1 and this carbon in double bond carbon 2, let's imagine 2 different possibilities. What if carbon 1 of the double bond grabbed the H? Well, if carbon 1 grabbed the hydrogen, then that would mean that carbon 2 has lost electrons. So carbon 1 here, it's losing a double bond, but it's grabbing hydrogen. So it keeps a full octet. Carbon 2 had a full octet, but it's not grabbing the H. So it loses a bond. That means it gets a plus charge. If that's kind of too complicated, the most important thing is to remember that whenever you have a carbon-carbon double bond and you attack a hydrogen like this, one of the carbons in the double bond gets the hydrogen. The other carbon in the double bond gets the plus. So this is one of our 2 possibilities. If carbon 1 got the H and carbon 2 got the plus. Our other possibility is double bond disappears. What if carbon 2 got the H and carbon 1 got the plus? So these are our 2 possibilities. Now let's talk about which one actually forms. So first things first, hydrogens, remember, are implied. I don't have to draw them in. So I'm going to redraw these structures without drawing in the hydrogens. So my 2 possibilities are this carbocation and this carbocation. Which one's more stable? Well, this one is a primary carbocation because a carbon with a plus is bonded to one other carbon. This is a secondary carbocation because a carbon with a plus is bonded to 2 other carbons. So remember what we said? Tertiary is better than secondary, is better than primary. So I don't have any tertiary, but I have secondary. So a secondary carbocation is immediately better than primary. So I'm not even going to consider primary. It's not even going to form. So that means I have this structure and I have the bromine minus structure here. So what I'm going to do is I'm going to redraw this step a little bit neater, and then we're going to go from there. And so let's see again, I have HBr. The first step is for the double bond to grab the hydrogen, and the bond breaks towards the bromine. So whenever this happens, you look at the carbon, look at the 2 carbons in the double bond, and you see where would it be most stable to put a double bond? Would it be on this carbon double bond, carbon 1 or carbon 2? And the more stable carbocation would be where carbon 1 is because it's secondary and you lose a double bond. And in this step, I made Br minus. So remember that positive and negative attract. So somehow the plus charge and the bromine are going to come together. So, and just like we said before, whenever we draw arrows in orgo, it has to come from the source of electrons. So I have no electrons on this plus charge, but I have electrons in this bromine. In fact, to follow the octet rule, this bromine actually has 4 sets of lone pairs. One of them is going to attack the plus. Remember, attack means forming a bond too. So if we think about this, I still have these 3 carbons here, but now the bromine is forming a bond to where the plus was. So this is going to be my product. Now let's think about where the charges went. So a plus on a carbon implies a lack of electrons, but now it gained electrons from the bromine. So if it was positive, our electrons are negative. So a negative charge is coming in towards a plus, which makes it neutral. The bromine, on the other hand, was negative, but it's donating electrons. It's getting rid of its electrons to give to the plus. So if it's getting rid of it, then that means that it's getting less negative or more positive. And so what's more positive than being negative? Neutral. So the rule of thumb for this is that whenever something attacks something else, it gets more positive. So for example, when the double bond attacked the H, this got more positive. When the Br minus attacked the carbon, the Br got more positive. It became neutral. So let's move on to another example of this. So let me take an alkene like this one, and this time I'm going to use HCl. So HCl is just the exact same concept as HBr. So the first step, just like before, is that the electrons in the double bond are going to attack the hydrogen, and the bond is going to break towards either the bromine, chlorine, iodine, whatever we have, just like before. So now I know that I'm going to get rid of the double bond. And so after I do that, I'm going to get a plus charge somewhere, because that's the rule. Whenever the double bond attacks the H, I'm going to get a plus charge at one of the two positions where the double bond was. So let's just call this carbon, carbon A, and this carbon, carbon B. So where would the carbocation go? So if we think about it, our two possibilities are my carbocation could either go on this carbon in double bond, carbon A, or it could go on carbon B. And it's going to prefer to go on carbon B because this is a tertiary carbocation, because the carbon with the plus is bonded to 1, 2, 3 other carbons, so tertiary. And if the plus one on carbon A, then it would be a secondary carbocation because the carbon with the plus is bonded to 2 other carbons. So it's never going to go to the less stable position when you have a carbocation. And so it's going to prefer this one, this tertiary carbocation. So after this first step, I also made Cl minus, just like before. In this case, I make Br minus after the step because the bromine is gaining electrons to become negative. Here, the chlorine is gaining electrons to become negative. So now I have this carbocation and the chlorine. And so one of the lone pairs from the chlorine, just like before, with the bromine, when it attacks the plus, same thing here, attacks the carbocation. And you're now going to form a bond between the chlorine and where the positive charge was, like this. And that's going to be your answer. Just like before, charges disappear. Okay, so the next thing we're just going to do is another example of this. So I encourage you to pause the video and try this problem on your own, including the mechanism and the product, and then look at the explanation. So for a problem like this one, again, I have a carbon-carbon double bond with HBr, HCl, or HI. First step is always the same. The double bond grabs that hydrogen and the bond breaks towards the iodine or the bromine or the chlorine. So just like before, I'm going to lose the carbon-carbon double bond. Now I'm going to put the plus charge at one of the two positions at the carbon-carbon double bond where it would be the most stable. So if the plus charge went here, it would be tertiary because the carbon with the plus is bonded to 1, 2, 3 other carbons. If it had gone here instead, it would have been secondary because if the carbon had gone here, then the carbon with the plus would have bonded to 2 other carbons. And so because tertiary is more stable than secondary, we're not even going to consider the secondary one. So this is my carbocation, and after this step, I make I minus, and then I attacks the plus, and then I'm going to wind up with my iodine there. Okay, so in that case, it's another example of double bond breaking to make a carbocation, and then the halogen attacking the plus. So we'll do one more example of this, and then we'll do some more complicated examples when we have to talk about carbocation rearrangement. So let's say I have a problem like this one, and I'm going to react this with HCl. So again, I encourage you to pause the video and see if you can figure out the answer, and then we'll go through it. So the first thing, just like before, is I have a carbon-carbon double bond. It's going to attack the hydrogen, and the bond is going to break towards my bromine, my chlorine, or my iodine. In this case, it's HCl, so chlorine. So just like before, I'm going to redraw the same exact structure without the carbon-carbon double bond. And now I'm going to choose which carbon that was in the double bond gets a plus. So if the plus went here, this would be a primary carbocation because the carbon with a plus is bonded to one other carbon. That's not stable. But if it went to this carbon in double bond, it would be a tertiary carbocation. And tertiary is much more stable than primary, so it's going to go tertiary. And now I have my Cl minus. So my Cl minus is going to attack the plus, and I'm going to wind up adding Cl to this position, and methyl is still there. And so this is how I get to my final product. Okay, so that's the basics of regular alkene reactions that go through carbocations. But now we have to talk about this concept of carbocation rearrangement. So here's an example of carbocation rearrangement. Let's say I have an alkene like this one. I'm just going to use HI. So based on what we've learned so far, it does make sense that the first step is that the double bond attacks the H and the bond breaks towards the iodine. So looking at this structure here, I get rid of the double bond, and now I have to choose where the positive charge goes. It can either go on this carbon in the double bond or this one. Well, it's going to choose this one because this one is secondary. It's not going to want to go primary. It's going to want to go secondary. So based on what I taught you previously, you might expect the iodine to then attack this. However, whenever you see a carbocation, you have to look out for carbocation rearrangement. So what does that mean? It means look at the adjacent carbons and see if there's a place that it would prefer to go to. So here's what I mean. I had a secondary carbon here, secondary carbocation here. It would not want to go here because then it'd be primary. But looking to the very left of it, if the carbocation were to move there, it would become tertiary. And remember, tertiary is more stable than secondary. So it's going to do that. We're going to talk about how exactly it does that in a second, but it's going to shift to where it wants to go. The carbocation was secondary, and now it's going to become tertiary. And again, we're going to go through this step in a lot of detail in a second, but now my carbocation is happy being tertiary. So then my I is going to attack the plus, and I'm going to get a product like this, where my iodine adds to the carbocation. So how exactly does this step work? Well, let's do an analysis here. So let's see how many hydrogens are on this carbon. Well, this carbon has no charge on it, which means it has to have a full octet, which means it has to have 4 bonds. 1, 2, 3. That means there's 1 implied hydrogen. Okay. How many hydrogens on this carbon? Well, a plus charge on a carbon implies a lack of a bond. It means there's only 3 bonds. 1, 2, 3. So that means there's 0 hydrogens here. So basically, I have 1 hydrogen here and 0 there. So how do I get rid of it? And the answer is you're moving the hydrogen to the carbon that had the plus on it. This carbon is gaining a hydrogen and a bond. That's why it becomes neutral at the end. This is called a hydride shift, where you're moving a hydrogen towards a carbocation. So how do we actually show this happening? Well, remember that every arrow in orgo has to come from a source of electrons. There's no electrons in the H itself, but in the bond between the carbon and the hydrogen, electrons are going to go towards the plus. So that's going to get rid of this bond here, making this carbon have a lack of a bond, which means a plus charge. This carbon is going to gain a hydrogen. Remember, hydrogens you don't have to draw in. Technically, this carbon has 1 H, and now it has 2 because it's gaining 1, but you don't have to draw in hydrogens. And so we're moving the hydrogen from here to here because we want the plus charge to go to the position where the hydrogen was. So let me actually redraw this without all of this in the way. So I'm at this carbocation here. I want to shift the plus to this carbon. Look at the carbon you want to shift the plus to. It's secondary. I want it to be tertiary. Look at the carbon you want to shift the plus to. See if there's an H on it. If there is, it's going to move the H to that position, and you can get a plus exactly where you want it to go. And again, this is called a hydride shift, one of the most important carbocation rearrangements. And so now I have a tertiary carbocation, so my iodine is going to attack the plus, giving me my product. So it's kind of a complicated type of problem. Let's do more examples of this. So let's say I have an alkene like this one. I'm going to use HBr again. So the first step of HBr, HCl, HI is always going to be exactly the same. Double bond attacks to H, and electrons break towards the halogen, the bromine, the chlorine, or the iodine. So when this happens, again, my double bond's going to disappear, and I have to decide now where I want the plus charge to go. It can either go on, it's basically going to have to choose which one it wants to go to, looking at the two carbons that are in the double bond. It can go primary or secondary. Those are the only two choices I have because that's where double bond is. And if it has a choice between primary and secondary, it's of course going to choose secondary. So now that secondary, you whenever you make a carbocation, always look to see if it can have a potential for carbocation rearrangement. So looking here at the secondary, it's not going to want to rearrange there because that's primary, but this is a tertiary position. So look to see if there's a hydrogen on the position where you want the carbon or the carbocation to be. I have one hydrogen on here, which is all I need to do a hydride shift. So I'm doing a hydride shift so that I can move my carbocation from secondary to tertiary. So you look at the position where you want the plus to move to, see if there's an H there, and if there is, shift it to where the plus previously was, and then the carbocation will go where the H was. Now my carbocation is perfectly happy being tertiary, so my Br minus is going to attack the plus, and you're going to wind up with a product like this one. Okay, so that's the concept of hydride shifts. Now let's talk about another type of rearrangement. So let's say I have a double bond like this one, and I'm going to use HCl. So again, first step, always the same. Double bond attacks the H, bond breaks towards the Cl, and now I have to choose where I want the plus charge to go. So of these two options where the double bond is, it's going to choose secondary over primary. So it's going to go here. Okay, now looking at this, again, whenever you see a plus charge, always look to see if it can do rearrangement. Is there a place the carbocation would prefer to be more than secondary? Okay, so first of all, it's not going to want to go primary. What about this position? So it would like to be here because there's a bunch of carbons around it. But remember what we do. You look at the carbon it wants to go to and see if there's an H on there. If there's an H on there, you move it. So on this carbon, carbon can only have 4 bonds. It already has 4. 1, 2, 3, 4, and they're all to carbons. So when you have 4 bonds to carbon, that means there's no H on there. So at first, it looks like there's nothing you can do. But whenever you can't do a hydride shift, look to see if you can do a methyl shift. So I have 3 methyls here. What if I move a methyl towards that plus charge? So here's what I mean. So I still have this carbon, and that carbon are still those 3. I still have this carbon and that carbon, but I'm moving one of the methyls to that plus charge. The reason I do this is because if I move the methyl there, now my plus moves to this position because this carbon lost a bond. It lost that methyl group, and so the methyl group is going to move over there, and now my carbocation goes to this tertiary position. Very similar to this example where you do a hydride shift, you're moving the H towards the plus, and then the plus goes to where the H was. You're moving the methyl towards the plus, and the plus goes to where the methyl was. And now I have a really nice tertiary carbocation. I have Cl minus is going to attack the plus, and now I'm going to get a chlorine at that position. Let's do another example of a methyl shift. So let's say I have a problem like this, and I'm going to react it with HI. So again, just like before, I have a double bond, and the double bond's going to attack the H, and I have to choose where the carbocation goes. The carbocation is going to go secondary rather than primary, and now I am here. So now that I'm here, again, look to see if you ever have a plus charge, look to see if there's a place that it wants to go better. So it's secondary now. It's not going to want to go primary, but it wants to be here surrounded by all these carbons. Are there any H's there? Well, carbon already has 4 bonds. 1, 2, 3, 4. That means there's no H's on there. So I can't do a hydride shift, but I can move the methyl and do a methyl shift towards that plus. Oh, and by the way, whenever I do the squiggly arrow, that's just like a rearrangement arrow. Unless your professor is really strict about arrows, it should be fine if you just do a regular arrow like this, but the way I was taught, I should do a little squiggly arrow like this when I do a rearrangement. So now that I'm here, I'm moving the methyl from this position, the tertiary, and it's going to be bonded to that what was secondary, now it's tertiary. And the plus is going to go wherever the shift occurred. Remember, the whole point of this is I want to move the plus there. So that's why I move the methyl and the positive charge goes there. It goes to wherever you lost the group. And now my I minus is going to attack the plus, and you're going to wind up with your product like this, where you're added your, in this case, iodine to that carbon. So before we move on to the next thing, which is going to be hydration, I'm just kind of give you some practice problems to work on. Pause the video and try these on your own, and then we are going to go through them all together. So let's say something like this. All right. And let's just react all of them with HCl just for simplicity. So try these problems. I'm looking for only the product, but if you're drawing the mechanism, that's totally fine too, because the mechanism is very helpful in figuring out the product. So I would encourage you to test out the video, and then we're going to go through these. So first things first, I have a double bond with HBr, HCl, or HI. So I'm not asking for the mechanism. So whenever you get a problem and they don't ask for the mechanism, they only want the product, it's okay to use shortcuts as long as it's sort of, you're being smart about how you use them. So for example, the first step of the mechanism is that the double bond attacks this and the bond breaks. But if you remember that in your head, you can think, okay, wait, I know that after the first step, my carbocation is going to prefer to go to the best position of the two carbons that were in the double bond. It's not going to want to go primary, it's going to want to go secondary. So I know my intermediate is this. Whenever you have a reaction that goes to a carbocation, I always recommend drawing out the carbocation intermediate to see about potential rearrangement. So now from here, I'm going to look to see where it can rearrange if it can at all. So it's not going to want to go primary, but it's going to want to go tertiary. So it's going to want to move to this position. So am I going to do a methyl shift? I have a methyl. Well, remember, the only time you do a methyl shift is if you cannot do a hydride shift. So do I have a hydrogen here? Well, carbon has 4 bonds, 1, 2, 3. That means I have 1 H on there. That's all I need. So even though I have a methyl, hydride shift always comes before methyl shift. So my H is going to move towards that plus. And so I'm going to move the H up there. Again, I don't have to draw the H in, but you can if it helps you. And the plus is going to move to the position that lost the H, exactly where I want the carbocation to go, tertiary. And so now my Cl minus that I made in the mechanism is going to attack the plus. And so I'm going to get my Cl added to this position, and you can really draw anywhere as long as it's off of that carbon with the plus. And so this is my answer for the first one. Now for the second one, we should draw a little line like this just to so we don't get confused. So in this one, again, let's try to draw out the intermediate without drawing the whole mechanism. My carbocation is going to prefer to go secondary rather than primary. So my carbocation is going to go here. Let's see if it can shift. Well, once you go here, are there any hydrogens it can shift? No. Carbon already has 4 bonds to other carbon. So I can't move a hydrogen. Can I move something else? Yes, I have a methyl. So again, just like before, you always look for hydride shift before methyl shift. But in this case, I don't have a hydride, I don't have a hydrogen, so I'll move a methyl. And so I'm going to move the entire methyl. So I had 2 before. That means I still have 1 left. My carbon, this methyl moves up there. And that means that the plus is going to move to the position where I lost the group, which is this carbon right there. And it's always going to go where we want it to go. My plus is there. The whole point of doing the shift was to make the carbocation more stable. It was secondary. Now it's going to be tertiary. And now that I have this tertiary carbocation, I have my Cl. And again, if I don't draw the whole mechanism out, I can think like, okay, now my Cl is binding to where the plus is. And so the Cl is going to go there. And that is my product for this one. Okay, let's do this last one now. So again, I have HCl, my double bond is going to attack. So now I'm going to look at the position where it would be most stable. So I have secondary or tertiary, it's going to want to go tertiary. So can it shift anywhere? Here secondary, here secondary, here secondary. It's already happy where it is. So it's not going to do any more shifts, and the Cl is just going to add to where the plus was. And this is going to be my product. Okay, so the next thing we're going to do is talk about the next alkene reaction. So in reality here, yes, we're talking about hydrohalogenation, but really we're talking about the whole gist of carbocation reactions in general. And so carbocation reactions are really important for the entirety of Orgo 1. And so that was basically, in order to learn carbocations, you have to do a reaction. What we're going to do now is go on to the next reaction that also goes through a carbocation. This one is called hydration. So hydration is the idea where you're adding an alcohol, an OH, to an alkene. So, for example, if I have an alkene and I'm going to be adding an OH to it, this is hydration. So there are actually a few ways you can add an OH to an alkene. The one we're going to focus on in this video is going to be hydration, one that goes through a carbocation. The reagent to do this is H3O+. Now, depending on what university you go to, they might write H3O+ in a different way. And that seems kind of weird because chemistry is chemistry, but in reality, there is no such thing as a bottle of H3O+. In reality, H3O+ is H+ mixed with water. Because if you think about it, I have two H's here. If I add another H, that's H3, and then I have O, and then a plus charge. So H+ with water is H3O+. H+ is written in a bunch of different ways. Most notably, H2SO4, HNO3, H+ on its own, or HCl. Now, the problem with using HCl here is that we already know HCl does something to alkenes. HCl is going to add to the alkene. So in future situations where you don't have an alkene, you're going to be seeing HCl in place of H+ a lot. But for the purposes of this reaction, you're either going to see it written as HCl+, they might have water in there, or one of these with H2O, because this is H+ and this is H+. Either of those would work. So we're going to mostly use H2O+, but I'm also going to give you some examples of these as well. So this reaction adds OH to double bond. So let's go over the mechanism for this one. It's very, very similar to the previous mechanism. So I'm going to redraw H3O+ like this, where I have OH2 and it's single bond to an H with a plus. So the double bond, just like before, is going to grab the H, and the bond's going to break towards the other thing, just like in previous examples. Double bond attacks the H, the bond breaks towards the other thing. So just like before, I'm going to get a carbocation, and I'm going to choose to make it secondary. What happens to this? Well, it lost the H because the H added here. Now it's OH2, and that's just water, H2O. And it was positively charged, but it gained electrons. When something's positive and it gains electrons, that makes it neutral. So I have water. So, but in the previous examples, you had a plus charge and then something with a pure minus charge. The minus attacked the plus to get to your answer. This one's similar, but a little different. In this case, there is no pure minus charge on the water, but it still has lone pairs. So the lone pair is going to attack the plus. Let's think about this. What's going to happen? So whenever you attack, you're forming a bond. So the O has a lone pair on it. It's forming a bond between the O and the carbon. So the carbon now has an O on it. The O attacked the carbon. But what's the O attached to? Well, remember, water really looks like this. It's an O single bond to two H's. So if this is what's attacking, the O is still attached to two H's like this. And so after it attacks the plus, I'm going to get OH2 attached to the carbocation, which is no longer there because this carbon gained electrons, so it became neutral. But what about the charge of this oxygen? Remember the rule. And I wrote it out somewhere. Whenever something attacks something, it gets more positive. So in the previous examples, we had a minus charge attacking the plus. It became more positive. What's more positive than being negative? Neutral. But when you have something already neutral, whenever something attacks, it gets more positive. The O attacked, it's going to have a positive charge on it because it was neutral to begin with. So this is not going to be our product because we don't like when things have charge on it. So what we're going to do is we're going to get rid of one of the H's and get rid of the plus charge. So how are we going to do that? So whenever you have H3O+, that implies you have a lot of water around. So another molecule of water is going to attack one of the hydrogens and the bond is going to break towards the oxygen. So let's think about this. I still have my O, I still have the H on the left side, but I lost the bond to this hydrogen because the bond broke to the O. O was positive. It gained electrons from this bond, and that made it neutral. Because when it's positive and you gain electrons, you get it's neutral. The H2O grabbed the H, and that means you're forming a new bond. The H2O is forming a new bond to H. That's going to make HCl plus, but no one really cares about that because this is our main product, the alcohol there. So basically, the mechanism is very similar to hydrohalogenation. The only difference is that it has one more step at the end. So let's do another example, and this time let's do some with the potential for rearrangements. So let's say I have a problem like this one, and I'm going to use H3O plus. And remember, H3O plus you might see written in many different ways. They might even write water with it. So just like before, if I have a double bond with H3O plus, let's do the mechanism as well. The very first step is for the double bond to attack the H. The bond breaks towards the oxygen. So if this happens, again, we're going to choose where we want the carbocation to go. It's going to want to go secondary rather than primary. Now it's here. So whenever I have a carbocation, I have to look to see if there's any potential for rearrangement. Well, it wants to go here. Are there any hydrogens there I can move? Well, carbon already has 4 bonds. 1, 2, 3, 4. 4 bonds to other carbon, I should say, which means there's no H's there. So I can't do a hydride shift. If I can't do a hydride shift, I look to see if there's methyl. I have a methyl shift, so I'm going to move the methyl towards that plus. And so now I have an ethyl still on, ethyl still on that carbon. I move the I move the methyl to this carbon. And now the carbocation is going to move to the position where the methyl left. So my plus is going to go on this tertiary position. And so the overall carbocation stability went from secondary to tertiary. Now that I have tertiary, remember, whenever you have HCl plus, you have the that implies you have water. I mean, you made water in that first step. Whenever you have HCl plus, that means that you have water, and water is what's going to attack the plus. When you have HBr, Br attacks. HCl, Cl attacks, etc. HCl plus, remember, HCl plus really means H plus with water. That means that water is what's attacking the plus. And so remember the rule, just like before, you are going to be adding oxygen to that carbon with a plus, because oxygen has a lone pair, but oxygen is still attached to 2 hydrogens. H there, H there. But remember the rule, whenever something attacks, it gets more positive. Water is neutral. So when it attacks, it's going to have a plus on it. And so then you're going to take another molecule of water, grab H, the bond breaks towards the O, and then you wind up with an alcohol. Whenever you have HCl plus with your double bond, you're winding up with an OH, an alcohol there. Okay, so we'll do one more example of this, and then we're going to move on to what we call a ring expansion, which is another type of carbocation rearrangement. And then we're going to do some what I think are really difficult problems in the next part. So one more example of this. Let's see. All right. So let's say I have a problem like this. And actually, I'm going to write H2O plus in a different way this time. I'm going to write it like H2SO4 with water. That's the same exact thing. So H2SO4 is your acid source, your H plus. So actually, before I write it as H2SO4, I'm going to write it as H plus. I'm going to show you like this, and I'll show you the first step as if it were H2SO4. So when it's H plus, it's kind of nice because all you have to do is this. The first step of making the carbocation, all you have to do is show this right here because they abbreviated H plus for you. And again, these are all ways of showing the exact same thing. If you have some acid, H plus, H2SO4, HNO3, with something else, the acid is being used to make the carbocation. It's going to want to go secondary more than primary. And now that I'm here, I have a secondary carbocation. It wants to go tertiary. Can it shift? Do I have a hydrogen on there? Yes, I do. So I'm going to do a hydride shift. The H is going to move towards that plus. And I'm going to wind up moving the plus to the tertiary position. The H added there, but you don't have to draw it in. And now again, whatever you have with the acid, this is HCl plus, the water, that's what's going to attack. The water is attacking the plus, and now I get an O. It's still a single bond to 2 hydrogens. And remember the rule, whenever something that's neutral attacks, it gets a positive charge. So then another molecule of water is going to come in, take away the hydrogen just like before, bond breaks with the oxygen, and I'm going to wind up with my product, which is an alcohol. Okay, so that's essentially the concept of hydration. Now, as promised, let's talk about how we would do it if I had H2SO4 with water. Remember, H2SO4 is H+. If you see H2SO4 or HNO3, those are H+. So how would you show double bond attacking H2SO4? So you would have to show H2SO4 written out at least preliminarily. So I'm going to write out H2SO4 like this, H2SO4. Double bond's going to attack the H, the bond breaks towards the O. But it's the same type of gist. Something's grabbing an H to make a carbocation. Okay, so we're going to move on to the next, that's the first step. So we're moving on to the next example of what we call a ring expansion, which is the next type of rearrangement. Then I'm going to give some practice problems for you to work on, and then move on to some trickier concepts. So what is a ring expansion? Well, kind of as the name sounds, you're basically taking a ring and it's becoming one size bigger. So let's do an example of this. First of all, ring expansions, at least for most professors, the rule is that you can only ring expand from a 4-membered ring to a 5-membered ring, or a 5-membered ring to a 6-membered ring. 6-membered ring is the most stable ring. So if you have a 6-membered ring, it's not going to shift to 7. So the most common example you see is a 4-membered ring to 5-membered ring, or a 5-membered ring to 6-membered ring. So let's talk about how you would even approach this type of thing. So I have a double bond with HBr. So as you learned, the first step is for the double bond to grab the H. So again, the carbocation is going to go to the position where I want it to go. Of the two in the double bond, it's going to want to go secondary. So based on what we learned so far, it's very tempting to say, okay, wait, I have a tertiary position here. Let's do a hydride shift from the plus there. However, if you have a plus charge, write this down. If you have a carbocation on the adjacent carbon to a 4 or 5-membered ring, it will ring expand. Okay, so here's what I mean. I have a carbocation here. Yes, it's tempting to put a tertiary, but if I have a carbocation on the adjacent carbon to a 4 or 5-membered ring, this one's 5, 1, 2, 3, 4, 5, it's going to ring expand. So how do ring expansions work? So whenever I do a ring expansion, I like to number my carbons, because it gets really tricky, in my opinion, to keep track of them if you don't. So I'm calling this carbon 6 and this carbon 7. So in a ring expansion, what's really happening is, let's take this bond between 1 and 5. You're breaking the bond between 1 and 5. 5 is breaking off from 1, and 5 is now attaching to 6. So what's really happening is the carbon that is adjacent to the plus, that is no longer attached to the carbon that's next to it. The carbon that, let's in this case carbon 5, is breaking off from 1 to attack carbon 6. So let's see what we have so far. So I like to draw it in this weird way at first to still illustrate that we have the same exact structure, but only one thing is different. So all I did here was redraw the exact same thing. I just didn't fill in this bond right there. So 1 and 5 are breaking. 5 is breaking from 1 to now attached to 6. So I know this was kind of weird, but this is how I like to draw it. 5 is now being attached to 6, like this. I'll draw a little better. And so, oh my God. All right, here we go. So if 5 is now attached to 6, I have a 6-membered ring. 1, 2, 3, 4, 5, 6. And that's where the ring expansion occurred. So we did a carbocation rearrangement. That means the carbocation moved somewhere. Well, where did it move to? Well, remember, the plus charge always goes to the position that lost a bond. Carbon 1 lost a bond. It was bonded to 5. Now it's no longer. Another way to think about it is that whenever you do a ring expansion, the plus is always going to move to the adjacent position, the first one that's on the ring. So the plus is there originally. After the ring expansion, it moves to the adjacent position that's on the ring, which is carbon 1. So now that I have this, I'm going to redraw this in a prettier way. I have a 1, 2, 3, 4, 5, 6-membered ring. So I'm going to draw a 6-membered ring. Doesn't matter where I put any group. I'm just going to arbitrarily put 1 there, 2 there, 3, 4, 5, and 6. And on 6, I have a methyl group, which is carbon 7. And on carbon 1, I have a plus charge. So now if I redraw this without all the numbers, I have a structure like this one. And you can always double check your work by counting the carbons. I have 7 carbons in the structure originally. You never lose any carbons or gain any when you do this ring expansion or any rearrangement, in fact. So I still have 7 carbons. Okay, great. So now it's time to think, okay, I have a carbocation. I have Br minus, let's attack the carbocation. But remember, always look to see if the carbocation has the potential to move. So even though I just did a rearrangement, a ring expansion, I have a secondary carbocation, and here's tertiary. It wants to go tertiary. So at first, like, okay, let's do a methyl shift. But wait, remember the rule: always look to see if there's a hydrogen first. It's tertiary. Do I have an H on there? Yes, I do. So hydride shift always comes before methyl shift. My hydrogen moves over. That's going to move my carbocation from secondary to tertiary. My plus goes here now. So now it's tertiary. It's as happy as it can be. And so now my Br minus is going to attack the plus, and you're going to wind up with your product. So I know it's kind of a long concept, but the more you practice, the more you'll kind of get the hang of it. So let's do another example of a ring expansion. So let's say I have this time a 4-membered ring, and I'm going to put it in a position like this one. So, and this time I'm going to use H3O plus, H plus with water. So again, first of all, I have an alkene with H3O plus. That means I know I'm adding an OH somewhere. So let's think about this. The first step is always the double bond attacks the acid, right? Attacks HBr, or in this case, H plus. Or if we have H3O plus, then H3O plus. It always, the double bond always attacks the acid whenever you have a carbocation reaction. So the carbocation is going to choose to go tertiary because it's not going to want to go primary. So even though it's tertiary, remember the rule. If you have a carbocation on the adjacent carbon to a 4 or 5-membered ring, it will ring expand. So even though it's tertiary, it's adjacent to a 4-membered ring, so it's going to ring expand. So just like before, I'm going to draw the ring expansion like this. Again, I'm going to arbitrarily number the carbons on my structure. I'm just going to, I'll call the carbons like this. And remember, what's really happening here is this bond is breaking. 4 is no longer being attached to 1. It's now being attached to 5. So if we redraw this, what we have so far, before I do that, so I'm just drawing everything except for this bond there. This is still 1. This is still 2, 3, 4. This is 5. This is, whoops, this is 6. This is 7. So I'm really forming a bond towards the plus from this carbon. So 4 is now being bonded to 5. So in that case, I have a 5-membered ring now. 1, 2, 3, 4, 5. I did my ring expansion. So where does the plus charge go? Remember, the plus always goes to the position that lost a bond. Carbon 1 lost this bond. Now it has a plus. Again, another way of thinking about it is that whenever you do ring expansion, it's always going to go to the adjacent position to where the plus was that would used to be on that ring. So my plus is here. The adjacent position that's on the ring was carbon 1, and this is carbon 1. So that's where it goes. So now I'm going to draw it a little prettier. I have a 5-membered ring now. Doesn't matter how I number it. In fact, I'm just going to number it in a really wacky way, just so that it doesn't matter how you number it. So if I call 1 here, then 2 is there, then 3, then 4, then 5. So on 1 is the plus, and on 5, I have 2 methyls, 6 and 7, 6 and 7. So now if I redraw this without all the numbers, what I'm really looking at is this. So now what can I do? Okay, I have a carbocation. Am I done? Okay, wait a second. Let's see if it can rearrange. It wants to go there. Are there any hydrogens it can move? No, I have 4 bonds already to carbon. So I have to do a methyl shift, not a hydride shift because there's no hydrogens available. And so I still have a methyl on there, but another methyl moved over. And because the methyl left, at that position, that's where the plus goes. And so we did all this work just to get to this carbocation. So now I have my carbocation. Remember, with HCl plus, water is going to attack. And the overall product is that you're adding an OH. So water is going to attack the plus, and then you're going to end up with OH2 with a plus charge on it. And then remember, we can't have it keep a positive, so another molecule of water is going to come in. So these are all the same reaction. It's just that the carbocation makes things very difficult. So this is the same H2O plus reaction. You make a carbocation, you attack the carbocation, and then you take away the H at the end, which is called deprotonating. But it's just that because you have a carbocation, you have to deal with all this rearrangement. And this is my ring expanded product. So I know this is a lot. We'll do more practice in a second, but that is the general gist. So a common question that I get from students is, why doesn't this ring expand? Right? This was 5-membered ring. And the rule was that if you have a 4 or 5-membered ring, it will ring expand. But that's only if you have a carbocation on the adjacent carbon to a 4 or 5-membered ring. It's not adjacent to it, it's on the ring. If it were here, okay, ring expand. If it were here, okay, ring expand. But it's not on the adjacent carbon to the ring, it's on the ring itself. So it's not going to ring expand again. And so that's why this is my product. Okay, so what I'm going to do is I'm going to give you some practice problems with this, and then we're going to move on to harder concepts with this type of thing, but same type of gist. So basically more complicated mechanisms is the thing I'm going for here. So let's take something like this. And so again, I encourage you to pause the video and work on these on your own. And then I'll go over it. Okay. So I'm going to do this one, and I'll do one more. All right. So I'm going to use this HBr. All right, so again, pause this and then try to figure out the answer. So for these problems, what we're gonna do is we're actually gonna try to figure it out without drawing the whole mechanism, just what we know, because in this case, I'm not asking for the mechanism, only for the product. So in order to figure out the product, whenever you see you have a carbocation reaction, which we do when we have a double bond with HCl plus or HBr, etc., see where the carbocation would initially form, and then see if it's gonna rearrange. So initially, my carbocation is going to want to go secondary, not primary. So now can it shift? Okay, wait. I have a carbocation adjacent to a ring. So your first thought is ring expansion. But remember, it can only ring expand if it's adjacent to a 4 or 5-membered ring. If it's adjacent to a 6-membered ring, it's not going to ring expand. So can it do another type of rearrangement? Well, is there a hydrogen there it can do a hydrogen shift with? No. This carbon already has 4 bonds to other carbons, but I can move the methyl. And so if the methyl moves over, it's going to go there. And now the carbocation goes to the place that lost the methyl there. And again, we're trying to do this without drawing the whole mechanism. And so I know HCl plus adds an OH. And so I'm going to be adding an OH to where the plus charge was. And the plus is there, so that's where my product is going to be. And of course, the real mechanism, if it helps you write the water attacks, you get the OH2 plus, and then another molecule of water comes in, grabs the H, and then you get alcohol. All right, let's try the next one. So this one, just like before, looks very similar, but it's a little bit different at the end. So I'm gonna get carbocation here still. Okay, but now I do have a plus adjacent to a 4 or 5-membered ring. This one's 5-membered ring, so it is gonna ring expand like this. So again, I like to draw it in a this form. I'm going to number this carbon 1, 2, 3, 4, 5, and this one 6. I'm not going to worry about this carbon and that carbon, but as far as numbering, this is still 1, this is 2, 3, 4, 5, 6. So whenever you do ring expansion, you're forming a bond 5 is no longer attached to 1. 5 is now being attached to 6. And so now where's the plus going to go? It's going to go to the carbon that was adjacent to the plus charge, the carbon that's on the ring, carbon 1 here, because that's the carbon that lost a bond. So this was kind of wacky, but I did a ring expansion. I have a 1, 2, 3, 4, 5, 6 membered ring. So let me redraw that in a prettier way. So it doesn't matter how I number them. I have 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. 1 has a methyl on it and a plus charge. 6 has a methyl on it. And then and now this is a rearranged structure. So now that I'm here, I'm going to see if my plus charge is going to rearrange anywhere else. And no, it's not, because it's already tertiary. It's not going to want to shift to an equally good position. Carbocation rearrangements only happen if you go into a better position. So my plus is going to stay there. I know with H2O plus, I'm adding an OH. And so my answer to this top one was here. And actually draw a little bit of a line there separate. And so I know my final product is going to be OH going to where the plus was, because my carbocation cannot shift anywhere else. And so this is going to be the product. My alcohol adding to that carbon. All right, now this one, HBr, I know I'm getting a carbocation at the position where it's most stable. So I'm going to get a plus charge here. Can it shift anywhere? Because it adds here first because tertiary is better than secondary. It's not going to shift because it's already tertiary. Okay, well, it would still do a ring expansion if it's tertiary if it were a 4 or 5 membered ring adjacent. Like in this example, it was tertiary originally, but still ring expanded because it was next to a 4 or 5 membered ring. In this case, it's just into a 6 membered ring, so it's not going to rearrange. And my BR is going to attack there. And so that's why my product is going to look like this. Okay, so this is the basis for basically hydride shifts, methyl shifts, etc., carbocation type reactions. So we're going to move on to the next thing, which is basically we're going to transition into harder mechanisms. Sort of a lot of professors will give you these as like introduction on the exam. For harder ones, we'll kind of go over how to go over those. But before we do that, we're going to talk about how carbocations work when they're adjacent to a benzene ring. So here's what I mean. A benzene ring, right, is a 6-membered ring with 3 double bonds in that, 1, 2, and 3. A benzene ring is very different than normal double bonds. So for example, let's say I have a problem like this one, I use HBr. Benzenes don't react with any of these alkene reactions you've learned. So these double bonds are going to stay. The reason is just because this is an Orgo 2 concept called aromaticity. Most Orgo 1 professors don't deal with that until Orgo 2, of course. But if your professor cares about it, it's because benzene is a stable aromatic compound. And aromatic compounds are so stable that if you reacted with a double bond, it would break that up. But as far as Orgo 1 professors normally, what they normally say is just know that benzenes don't react like normal double bonds. But this double bond is outside of the benzene ring. So that one will react like normal. So I'm going to get a carbocation. Where's it going to want to go? Not primary, it's going to want to go secondary. Okay, can it rearrange? The answer is no. Whenever you have a plus charge adjacent to a benzene ring, that's it. It's not going to rearrange anymore. You're not going to do any resonance. There's no hydrogen. You're not going to do any ring expansion or anything like that. If it's next to a benzene ring, it's just going to be happy there. We'll talk about why in a second. Then my Br minus is going to attack the plus. And so you're going to wind up with this product. Okay, this seems pretty normal, right? Okay, well, what if I change up the problem a little bit? At first, it looks almost the same, but it's actually a little different. Let's talk about why. So let's say I have a problem like this one. And I'm going to use the same reaction, HBr, or whatever halogen I used last time. So again, just like before, the double bond's going to type the H, bond breaks. So at first, looking at this, it's like, okay, wait a second. The plus charge is going to be more stable tertiary. However, the plus is actually going to form here. Now let's talk about why. So this is not secondary. This is called a secondary benzylic carbocation. When a plus charge is adjacent to a benzene, that's called benzylic, and it's very stable. In fact, secondary benzylic is more stable than a tertiary carbocation. The reason is because of resonance. If you imagine a double bond moving towards a carbocation like this, double bond moves there. This is the carbon that lost electrons, so you get a plus there. You can do resonance around the entire benzene ring. Remember, resonance is one of the most important concepts in orgo. If something can do resonance, that means it's stable. And so what that means is that this intermediate is so stabilized because it can do resonance all around the benzene ring like this. And so secondary benzylic, even though it's secondary, it's more stable than tertiary because of all the resonance it can do. So that changes how we look at problems like this, because now whenever you see a benzene ring and it has a carbocation, you have to consider, to your all the resonance forms, you have to consider how that plays in. So what you really have to know is that whenever you have a problem like this, the plus charge wants to be closer to the benzene ring. And so my plus charge is going to want to be secondary benzylic, not tertiary. And so now, believe it or not, this is more stable than that. It looks kind of weird at first, but this is more stable than this because this is next to a benzene ring. And then my BR is going to attack there. And so that's why my product is going to be this. Okay, let's do another example of this concept. So let's say I have something like this. Okay, and so I'm going to use HI. We haven't used that one in a while, I think. So HI, so I have a double bond. Again, the double bonds in benzene don't react. So this double bond grabs H, bond goes to the iodine, and you're going to get a carbocation. Where is it going to go? Well, it's always going to go at the most stable position, just like before, same as before. It wants to go tertiary rather than primary. Okay, so at first it's like, okay, wait, it's not going to rearrange. But wait, it wants to be closer to the benzene ring. So can it shift? Well, I have a methyl, but I also have an H. So I'm going to do a hydride shift. And I'm going to move my hydrogen towards there so that my plus goes next to the benzene. Remember, being next to the benzene for a carbocation makes it really, really stable. And so this is tertiary benzylic, which is one of the most stable carbocations ever, because one is tertiary and it's benzylic. Now my iodine is going to attack the plus, and you're going to wind up with this product, the iodine adding to the tertiary position. Okay, now benzylic is not always more stable. So sorry, I'm out of slides to go to the beginning. So for example, let's say I'm comparing a carbocation like this one. I have a primary benzylic, primary because the carbon with a plus is bonding one other carbon, as next to a benzene. So primary benzylic is not as stable as tertiary. Tertiary is still a little bit better than primary benzylic. So it was kind of getting jumbled. Let's draw out the whole list of carbocation stability in order. So the worst carbocation ever is going to be a methyl carbocation. A plus on a methyl, this is going to be the worst one. The next worst is going to be primary carbocation. Okay. After that is going to be secondary carbocation. After that is going to be primary benzylic. So a primary benzylic carbocation is more stable than a secondary carbocation. Okay, then it's tertiary. Tertiary by itself of a carbocation is more stable than primary benzylic. And then you have secondary benzylic and tertiary benzylic. So there's nothing more stable than tertiary benzylic. But the rule of thumb here is that everything's as you would expect. The benzylics are all more stable than non-benzylics, except tertiary is better than primary benzylic. So most stable on the right, least stable on the left. Let's do one more practice problem with this, and then move on to the next thing. So let's say I have my benzene ring. And also remember, benzene is abbreviated as pH. So if you see a problem like this one, that really is, that's the same thing as this. And so don't be fooled by the pH, it's just the same exact thing, it's just this. So if it helps you, redraw it out. And so I'm going to react this with H3O+. I know H3O+ adds an OH. So let me draw out my initial carbocation. I'm only looking for the answer, not the mechanism. But of course, if the mechanism helps you, go for it. So my initial carbocation is going to want to go tertiary rather than primary. But then I have tertiary. Okay, remember, this is secondary benzylic. Secondary benzylic is better than tertiary. So it's going to want to go there. Can it? Yes, it can, because I have a hydrogen I can move. I have actually two H's, but I have at least one. So I can do a hydride shift. And now I have a plus there. And I know H2O plus adds an OH where the final plus is. And so that's what my product is going to be. Okay, and that's just for more complicated type of rearrangement. At the very end, I'll give you some practice we're going to work on. But what I want to do now is transition into the next concept. So imagine I have a problem like this one. And I'm going to react it with something like this. So I have H plus, remember, which is an acid. And this time I'm going to react it with an alcohol, such as ethanol. So we haven't talked about this reaction specifically. Let's try to figure it out based on what we know. So we know that if I have a double bond with an acid, the first step is that the double bond attacks the H. And then you're going to wind up with a carbocation where it would be most stable. So I'm going to redraw it without the double bond, and my plus is going to go tertiary. Okay, is it going to shift? Well, at first it looks like it's not, because this is tertiary and I have two secondaries. But remember, this is secondary benzylic because it's next to a benzene. And when something is benzylic, remember that secondary benzylic is more stable than tertiary. So it's going to want to shift to that position. I have a hydrogen there. I actually have two. I'm going to shift one of them to do a hydride shift. And so now I'm going to get a plus there. So now what's going to happen next? So I don't have water this time to attack the plus. What do I have? This time I have an alcohol, but it's still the same gist. The O is going to attack the plus. And then, just like before, I'm adding the oxygen to the plus charge. So the O is attacking the plus. So the O is bonded to an H still, right? Remember this O is bonded to an H. And it's also bonded to these two carbons. Nothing is changing but in what's bonded to the oxygen in relation to this group. So the O still has an H on it and an ethyl group on it, two carbons after it attacks. But remember the rule, whenever something attacks, it gets more positive, so it has a plus charge. And again, just like before, we don't want things to end with charges. So we're going to take another molecule of the alcohol to come in, grab the hydrogen, the bond breaks, and what do we have after this? Let's think about it. What functional group do we just make? So we have an O, we lost the hydrogen, the O is still bonded to two carbons. Now this is an ether. Remember, an ether is an oxygen single bonded to two different carbon groups. So when I have H plus with water, we're making an alcohol. Because if I have H plus with water, you can think about it like this. You're losing one hydrogen. So losing one hydrogen from H2O, you're adding an OH. Here you're losing one hydrogen too. If you're losing an H from this thing, you're going to have O with whatever carbons it was attached to, like this. Let's do another example of making an ether. So let's say I have something like this, and I'm going to use H plus. And remember, H plus is the same thing as an acid, as a generic acid like HNO3 or H2SO4. So let's use that. And I'm going to react it with this alcohol here, isopropyl alcohol. So again, here I'm not looking for the entire mechanism. Let's think about the very first step though. I have a double bond with an acid. Remember, HNO3 is the same thing as H2SO4, which is the same as H plus. So just like before, right, the double bond's going to attack H plus to get a carbocation. So the carbocation is going to form secondary rather than primary. So it's going to go here. So can it shift anywhere? Well, this is, it wants to go there. There's no hydrogen, but I have a methyl. So I'm going to methyl shift. And I have the ethyl there. My methyl is going to move to where the plus is. If the methyl moves there, I get a plus where the methyl was. And now the O is going to attack the plus. And so just like before, I'm forming a bond between the oxygen and the carbocation. So the oxygen is here. It's still bonded to an H. And this isopropyl group, remember the rule, whenever something attacks, it gets more positive. It's a plus. And then just like before, we need to get rid of the H. So another molecule of alcohol is going to come in, grab the hydrogen, bond breaks towards the oxygen. And you're going to wind up with your product. So it's just the same exact process. It's just that you happen to be adding a different thing. So let's take this possibility and let's try a mechanism. So when I say mechanism, I mean a lot of times on an exam, there's going to be a specific question that says mechanism, and they'll give you the starting material, they will give you the final product, and they'll give you the reagent. And you have to show all the steps in order to get to the product. So let's say you're given a mechanism like this one. So normally, when I see HCl plus double bond, I'm thinking, okay, I'm going to be getting a carbocation, I'm adding an OH. But looking at this, that's not what's happening here. So whenever you see a mechanism question, you're basically trying to figure out how to get from here to here using only the reagent you have. So let's take an example like this one. I have H3O plus. So looking at the final product here, it's a cyclic structure. It's in a ring. I don't have that here. So whenever you're forming a ring, that means a molecule is attacking itself at some point. So here's what I mean. So you see how this carbon here has two methyls on it. 1, 2. That is this carbon right there. This carbon right here has two methyls, 1 and 2. So what that means is that this carbon somehow needs to be bonded to the oxygen in the final product. Now, the oxygen is not even close to being bonded to that carbon. So what that means is whenever you see an atom like an oxygen or a nitrogen or a sulfur, whenever you're making a ring, and the first thing to do is look at what carbon it needs to be bonded to, that it is not already bonded to. So I'm going to number my carbons. I'm going to say this is 1, this is 2, this is 3, this is 4, this is 5. So I know that carbon 1 is this one because carbon 1 has two methyls on it, and this is carbon has two methyls on it. This has to be 1. 1 is attached to carbon 2, which is attached to 3, which is attached to 4, which is attached to 5. And that makes sense because carbon 5 originally was bonded to the oxygen and it's still bonded to the O. So what's really happening here is that the O is somehow bonding to carbon 1 and losing the H. So this can get kind of complicated, but the overall gist is to first see, okay, what type of arrow am I going to have to draw? So because O is being bonded to carbon 1, that means somewhere in the mechanism, I'm going to have to do something like this. The O is going to have to attack that carbon eventually. Now, this is not the right step, but you're going to have to do something like that in the mechanism. Because whenever something is bonding to something else, it's because the thing with the lone pair is attacking that position and adding a bond there. So here's what I mean. Let's kind of do this example, then we'll do another one. So first things first, though, is that I'm getting rid of a double bond. How do I even do that? Well, remember, I have a double bond in acid. The first step is most likely going to be the double bond attacking the hydrogen. I have H3O plus in acid, so I'm going to get a carbocation. So where's my carbocation going to form? So naturally, we want the carbocation to form tertiary. So the whole point of making carbocations and all of these reactions is so that something could attack the carbocation. So what if instead of a water molecule attacking the plus, what if the oxygen attacked itself? Attacked itself at this position. Remember what we said, that whenever you have a linear chain and it's making a cyclic structure, that really means that the molecule is attacking itself. So I know we said that the oxygen has to bond to carbon 1 somehow. This is how it happens. It needs to have a carbocation first, and then now the oxygen can attack this carbon. And that's going to form a cyclic structure because the O is still attached at this position and now it's attaching at that position. So let's think about the structure here. I'm going to be making a 6-membered ring because I have 5 carbons, 1, 2, 3, 4, 5 in the structure. Oxygen is going to be part of the ring as well because it's bonding there. So I'm going to have a 6-membered ring with 5 carbons. O is still attached to carbon 5. It still has an H on it as well. 5 is attached to 4. 4 is attached to 3. 3 is attached to 2. 2 is attached to 1. 1 has 2 methyls on it, but no longer a carbocation. Just remember the rule, whenever you attack a carbocation, it disappears, and the thing that attacked, that's more positive. And so it can be tricky trying to visualize how rings form. So it's really valuable to look at the final product to let that guide you. So in this case, it attacked itself. I have this, and then I have to get rid of the H, just like before. Whenever something neutral attacks, it gets a plus charge. Neutral attacked, gets a plus, and then something's going to have to take away the H. What do I have? H3O plus implies the existence of water, a bunch of water. And so H2O is going to deprotonate, which means take away the H, and you get to your final product. And I get a cyclic ether. It's basically the exact same thing as this. Make a carbocation, oxygen attacks, and then something takes away the H. It's just that it's very a little more difficult because it's making a ring. I make a plus, it's making a ring, so it attacks itself at the plus. That makes a ring, and you take away an H. Let's do another example. So I'm going to do a molecule like this one, and 1, 2, 3, 4, 5. Okay, so I'm going to say, all right, let's provide the mechanism for this reaction. So I'm going to say that we are trying to get to 1, 2, 3, this. Okay, so again, this looks really kind of wacky, but let's do our overall analysis first. So I'm getting rid of the double bond. I already had one ring, I'm making another ring. The oxygen is part of the ring. So let's see what the oxygen is bonded to. So it was bonded to one carbon group there. Now it's bonded to carbon and carbon. So looking at this, does it make sense that this carbon, that's where the oxygen is being bonded to, that it no longer was before, because the oxygen was attached to a carbon coming off the ring, but it was not attached to this ring, which is this carbon in that ring. And it is in the final product. What that tells me is that somewhere in the mechanism, I have to do something like this. My oxygen is adding, it's bonding to that carbon, which means I have to show an arrow like this, somewhere in the mechanism. For example, like in this one, my oxygen was attacking the plus, something like that. Now, the real way to do this is we have to make a carbocation first. Remember, things with lone pairs like to attack carbocations. So my double bond is going to attack the H plus just like before. It's all the same type of chemistry, just a little bit difficult when it comes to ring formation. So just like before, I want to make my carbocation tertiary. And even if it didn't make logical sense as far as where it needs to go, let the product guide you. Even if it goes against some things that you might think, remember the product is what you're trying to get to. So how do I get to this? Well, I need the O to form a bond there. So I need to make my carbocation there so that my oxygen can attack. And so let's think about this. My oxygen is attacking there. That's going to be a 1, 2, 3, 4, 5-member ring. And look at this, 1, 2, 3, 4, 5-membered ring. So let the product guide you. It's all the same thing. This carbon is now being bonded to an oxygen. Between the oxygen and this carbon, I have 3 more. 1, 2, 3. So 1, 2, 3, bind to there. And remember the rule, whenever something attacks, it gets more positive. I still have an H on there, so I have a plus. And then a water molecule is going to come in to deprotonate it. And so this is a type of thing, this type of concept is very common in Orgo 1 and Orgo 2. The idea of carbocations, attacking carbocations, and deprotonation and positive charge. So I'm going to actually give you one, see if you can try to figure it out on your own. and then we will go through it together. So I'm going to say I have this 1, 2, 3, 4, 5. Whoops, I need to get rid of the carbon. Okay. All right, so again, I'm going to use H3O plus, and I'm going to ask you to provide the mechanism to go from this to this. And take your time, and then pause the video, and then we'll go through it. So looking at this, again, we're making a ring. That means that something is going to have to attack itself. So looking at this, I have a sulfur in the middle this time. Okay, well, that makes sense because I have a sulfur there. So the sulfur needs to attack a carbon, needs to be attached to a carbon that has 2 methyls on it. That's this carbon. That's the only carbon on this molecule with 2 methyls. That's how I know that's attacking at that position. So somewhere in the mechanism, I have to do something like this. But again, so far, the only way we know really to attack is if it's attacking a carbocation. So I need to make a carbocation. But wait a second, double bond is not there. I can't just make a plus charge immediately at that position because a double bond is there. But I know that I need to be making a carbocation. But remember, if I have a plus charge here, I can shift it there. So my first step is going to be my alkene grabs the H from H3O plus, the bond breaks. And even though they're both secondary, remember, we're letting the product guide us. I know that my sulfur is attaching to the carbon with the 2 methyls, so it has to go there. That means that of my 2 options where the plus could go here or here, it's probably going to go on this one so that it can easily shift to that position. Now it's secondary, I can do a hydride shift. And now I'm going to get a tertiary carbocation. And now that I'm here, now I can cyclize the molecule. The sulfur can attack the plus, and now it's going to make exactly the ring I need. With one difference, remember the rule, whenever something attacks, it gets more positive. So my sulfur has a plus. I have H2O, which is going to come in to take away the hydrogen. And so this is the general type of gist of reaction types you will see. Different type of mechanisms. Basically, they all have the same type of gist. It's just that they're a little bit different. So with the last few minutes, I just want to do some overall practice of what we did so far. And so I'm just going to kind of give you some random stuff. Again, I encourage you to pause the video as we do this one by one, and then we will go through them together. And again, I'll make some, I'm not going to tell you the difficulty, of course, of these. I'm just going to kind of do random problems, and then I'm hoping we're just going to go through it together from there. So the first one, I'm just going to say I have HCl with this molecule. So let's go through this one. So again, for all these, I'm only looking for the product. If the mechanism helps you, go ahead. Remember, this is a carbocation reaction. That means that I'm going to get a plus charge at one of the 2 carbons the double bond was. Is it going to go primary or tertiary? Definitely tertiary. Is it going to shift? Well, no, because tertiary is the best unless there's a benzene ring. This is not a benzene. Remember, benzene is when you have 3 lines in a cis-hemi ring. If it were this, then it would want to be tertiary benzylic. But it's not that, just a regular cis-hemi ring, so it's going to be happy being tertiary there. Oops. And now we're adding the chlorine to the plus charge. So Cl is going to add there. All right, let's do another one. This time, I will make it a benzene. It's kind of a weird example of a problem, but it still works. So this time, I'm going to use H2SO4 with an alcohol. I'm going to use methanol. Just remember the rule. If I see H2SO4, that's the same as H+. Where H+ is an acid. So double bond attacks the H+. And I'm going to wind up making a plus charge at the most stable position. So of tertiary and secondary, it's going to want to go tertiary because tertiary is always better than secondary. Is it going to shift? At first, it looks like it's not, but remember, if it goes here, it's next to the benzene ring. and secondary benzylic is better than tertiary. So it's going to do a hydride shift and become secondary benzylic. And so now that it's here, it's the most stable carbocation. So now what's going to attack? The only thing I have, MEOH. So H2SO4, H2O3, they never attack. The other thing that you have is there with it is going to attack the carbocation. And so now, just like before, I'm adding an oxygen. And so I'm going to wind up, oops, with a structure like this one. So my O is attacking the plus. It still has an Me on it, which is methyl, and H on it. Whenever something attacks, it gets more positive. And I need to take another molecule of alcohol to take away the H. Just like before, so I don't have any water around, I have a bunch of alcohol around. And so my methanol is going to take away H, and I end up with an ether. And so my product is going to be OMe, which is O with one carbon, and then this. Okay, let's move on to the next one. So the next one, I'm going to say, let's kind of do something ridiculous just to illustrate the point here. Let's say I'm going to use, let's just do HI. So this time I'm asking for the full mechanism, so let's go through it. Double bond attacks to H, bond breaks. And so I'm going to get a plus at the secondary position. So it can't ring expand yet because the plus is not adjacent to the 4 or 5 membered ring, but it's secondary. It wants to be tertiary. So we're going to do a hydride shift to make it tertiary. And now, even though it's tertiary, remember the rule, if you have a plus charge adjacent to a 4 or 5 membered ring, it's going to ring expand. So the ring is going to expand like this. Again, I like to number my carbons to illustrate exactly how it's happening. So I'm going to redraw the whole entire thing. I'm just not going to fill in that bond. So remember how this works with ring expansions. 1 is no longer binding to 4. 4 is now binding to 5. And that's what expands the ring. Now it's a 1, 2, 3, 4, 5 membered ring. The plus charge always moves to that adjacent position on that ring, carbon 1. That's a carbon that lost the bond. Carbon 1 was bonded to 4, now it no longer is, so it lost a bond. Now I'm going to make this a little bit prettier. I have a 5 membered ring. Doesn't matter how I number it, 1, 2, 3, 4, 5, as long as I'm consistent. Carbon 1 has a plus. Now, what does 5 have? 5 has a methyl group, which is 8, and an ethyl group, which is 6 and 7. So if I redraw this without all the numbers, I have this. Okay, so it's tempting to say, okay, let's put the iodine add yet, or now. But remember, always look to see if there's more rearrangement possible. This is secondary, but it wants to go there. Is there an H that can move to do a hydride shift? No, there isn't. So it's going to do a methyl shift. And so I'm going to move the methyl there. My ethyl is still there. And if I'm moving the bond there, my plus is going to go here. And now my iodine can attack. And now I'm adding my iodine to this position. And that is how you do a problem like this one. Okay, let's do a couple more and I think we will call it a day. So for this one, I'm going to, actually, you know what? I'm going to make this one a little bit tricky. So let's say I have something like this, double bonds, 2, 3, 4, whoops. 1, 2, 3, 4, 5. Okay. Let's say I have something like this, a hypothetical mechanism, and I'm going to use HCl plus. And again, I want the mechanism for this. So my product is going to look something like this. And I'm asking to draw the mechanism to explain how this works. So looks really wacky at first, but let's do an analysis. So first of all, what's doing the attack? Well, I'm making a ring and O is in the ring. That's how I know that the O is attacking, because nothing's happening to the N. The N, if it attacked, that would be in the ring. Remember, whenever you're making, doing reactions that forms a cyclic structure like this, the thing that's in the ring, that's part of the ring, is what's attacking. So I know the O is attacking somewhere. So where is it attacking? So it's attacking at the carbon with the nitrogen. This is because the carbon with the N is also the carbon with the O. That means the O has to somehow be attacking this carbon. So somewhere in the mechanism, I need to do something like this, O attacking the carbon with the N. The problem is, though, let's think about this. So I knew I did before is making a carbocation where a double bond was. I know I'm getting rid of double bond. So double bond attacks H, the bond breaks. And I'm going to wind up with this structure. Now, where does the plus go? Well, here's where it gets tricky. So looking at this, I need the plus to be on the carbon with the N. But at first, it's like, wait a second. Wouldn't it rather be tertiary? Why doesn't it go there? So whenever you get a mechanism question, I know it sounds weird, but let the product guide you no matter what. I know that the oxygen needs to be bonded to that carbon with the N. So even though it at first doesn't make intuitive sense that the plus is there, or the plus is not there, I know the product is asking the O to bond to that position. That means the plus must be there. And so the O is attacking there. And after the mechanism, I'll explain why it actually forms there. But the point of me doing this is to show you that sometimes mechanisms just happen, even if it's a little bit different than what you might expect. And so if it's attacking there, it's forming the ring. I still have the NH2, but the O still has an H on it. And whenever something attacks to get a plus, it's forming a cis-membered ring because the O is attacking there. I have 1, 2, 3, 4, 5 carbons. The O is attacking. And now HO plus implies I have water. So water molecule is going to deprotonate the H. So the real reason the carbocation would form here is because this is stabilized by resonance. Remember, resonance is movement of electrons. And so resonance is really important. It's movement of electrons in a given molecule. And so resonance stabilizes structures, stabilizes intermediates. So this carbocation is really stable because it has resonance capability, while this carbocation, even though it's tertiary, has no resonance. And so that's why if you get a mechanism like this, it's because of that. But again, the point of this is mostly to show that when you see a mechanism, let the product guide you. Okay. I think we will do one more, and then I think we'll call it a day for this type of thing. And so trying to see if I can make this. Okay, let's kind of do a really wacky one. So I'm going to do this, this, and this. Okay. This is kind of a ridiculous type of question, but kind of fun. So looking at this, I have a double bond with HBr. So in this situation, I want the product. So let me think about this. Okay, my original carbocation is going to go at the carbon that was part of a double bond. That's the most stable. So it's going to go secondary. Okay, can I shift? All right, yes, it wants to go tertiary. So it's not going to methyl shift because I have an H. All right, and now it's going to go to this position. So my ethyl and methyl are still there. My plus move there. Is it going to shift anymore? It's tertiary, but notice it wants to go there so it can be next to the benzene ring. So it can be tertiary benzylic. Is there an H that it can move? No. I have a methyl, so it's going to methyl shift. I'm going to move the methyl. And so the whole methyl is going to move to that position. I already had one methyl there. I'm adding another methyl. The ethyl is still there. And this carbon lost the methyl, so it gets a plus. And now it's not going to shift anywhere else to tertiary benzylic. And then my Br is going to be adding to this position. And I'm going to get a final product like this one. Okay, so I'm actually gonna take the last minute or two to do a couple of notes on some miscellaneous small type of things that your professor might care about. But even it's regular chemistry, but sometimes professors stress that, sometimes they don't. But I want to make sure I do talk about them because some of them are important. The first one is, let's say I have a problem like this. I have a problem like this one. Actually, you know what? Let me even make it a little, okay. I have something like this. I'm going to use, let's just say HBr. So my initial carbocation is going to go here. So the question is it going to shift? So at first it's like, okay, wait a second. It wants to go tertiary. So can a hydride shift and a hydride shift? And the answer is no. Carbocations are not all knowing. They only know what's next to them. So it only knows primary and secondary. It doesn't know that there's tertiary there. Now, if I had this, okay, now it knows there's tertiary, so it's going to shift. So if I have a problem like this, even though a carbocation would be more stable there, it's not going to shift there because it only knows what's next to it. So my final product would be a Br at that position like this. And so carbocations, again, are not all knowing. They only know what's next to them. That's kind of an example, something like this. Another example, let's say I have this, and I'm going to use HBr again. So my initial carbocation is going to form here. So it wants to ring expand if the plus were here, so it's a 4 or 5 member ring. But the plus is never going to go there. It's already secondary. It only knows what's next to it. It knows there's a plus, or it knows there's secondary there. It's not going to go to equal stability. So the bromine is going to attack there. Now, if I had something like this, then it would hydrogen to the tertiary and then ring expand. But because it only knows what's next to it, this carbocation here is equally stable. It would be in this carbocation's eyes because it only knows what's next to it. And so it's not going to rearrange. And so my Br is going to add here. Now, another thing we didn't talk about in this video is stereochemistry. So when I'll probably say that for another video, but when you have a carbocation and something attacks it, you're going to get what we call a racemic mixture. A racemic mixture means you get a 50-50 mix of dashes and wedges if you have a chiral center. So for example, this one below, this is a chiral center. A chiral center is one carbon that's single bonded to 4 different things. Methyl, this entire chain, a bromine and an H, so it's chiral. Because it attacked a carbocation, oops, what that means is, oh no, okay, yeah. What that means is that you're gonna get a 50-50 mixture of the bromine adding on a dash, and it's an enantiomer. Bromine adding, oops, follow down here. Bromine adding on a wedge. So I'm probably going to save stereochem for a different video because there are other alkene reactions that are specifically syn addition, anti-addition, and we'll review stereochem here. So yeah, if you have any questions, let me know. If you want to schedule a tutoring session, my information is in the link below. All right, thanks.